Hello, guys. How are you feeling?
Hey, we are great.
Hey, we are great. Yes, thank for having us.
Yeah, so good actually.
Okay, sounds good. I have a question for you. I read the description of the talk and it sounds interesting. Can you say a few words how you did arrive to the talk?
Okay, so Artem found us in Twitter, and that's it. We started talking, and it was great, and we decided to go ahead.
Okay. Any questions, Artem?
Yeah,
Yes.
actually, I want to tell a small story if I have time, and seems like I have a time. That actually someday I remember that I found this project inside the discussion of compiler development Telegram chat. Also, it's a cool chat. So you can join it. And I decided to play around with the solution, and I was so impressed that I decided first of all try to contribute a little bit in the project. I hope I will do it after the call, but also I decided to speak with guys and talk and request there to join us at the conference. And I think it will be so cool talk with so cool solutions. You will see it. Yep. And let's see what the guys will provide.
Thank you so
us.
much, Artem.
Yeah,
Thank
it's
you.
a
We are
cool
flattered.
story.
Yes.
Okay, I think let's do this. Have a good talk, guys.
All right. Thank you. Okay, let's start. Today, Vicente and I are going to talk about the tool we've been working on together. This is us, but you already saw our faces. Let's talk about the history of how we started working on this solution. Some years ago, we were developing an MMORPG game. Vicente built the game engine and the C language, and he did all these engine in C language. And I did the interfaces and the graphics. You can see this is what the state of the game reached, and you can see the terrain there. At the certain point of the process of developing this game, two things happened. One, we needed to grow our team because we needed more developers to join our journey, and the other was to have developing this game in a different set of languages, right? So can you imagine doing the quest engine in C or C++? It would be a nightmare. So we decided to go with another approach, and in order to code faster, we thought that we needed some kind of scripting. And at the moment, I was good at JavaScript, and we started thinking that maybe we could include scripting into this game engine. But apart from the game, we saw that there are other problems that we faced, or we knew people were facing. That's, for example, to do gradual migration of legacy code. We have developers that from PHP land that we know that they struggle when trying to migrate their code, and it will be great to have something to do exactly that, to do a migration to a more modern environment. So another problem that we saw is that the use of libraries from another languages is a little bit difficult to do. For example, Docker API. It is done in Go and Java, and it will be nice to have it on, for example, Node.js, right? For embedding scripts into game engines, this is what we talked before. And for example, Blender has their own scripting method that is with Python, but doing with other languages will increase the usability of Blender. The other example is, for example, libsec.com, that is a Linux interface for sandboxing that is only ported in Python, and we could use it on Node.js if we had such a thing. So after seeing all these problems, we realized that polyglot programming was the name of what we will start doing here. So what and why is polyglot programming? First, polyglot programming is the practice of using different programming languages into the same code base, right? When facing with technical problems, being agnostic of the language, using polyglot programming enables you to pick the best tool for the problem or for the job. You break the problem into several smaller components, and then you pick the best suitable language for it. For example, using toolings or libraries from other languages, or mixing low-level and high-level without boilerplate. But okay, this looks awesome in theory, but in reality, it requires a lot of boilerplate that you need to do, right? You need to create the connector between those languages, and then you need to create a protocol in order to send the information from one to the other, the types and such. So it is most likely that you end up implementing the solution in your main language. That's something that we saw people do. Also, we are aware that the companies struggle trying to scale teams or find the right talent to fit their stack. It will be good for them to just pick a developer and insert it into their teams. In order to scale multidisciplinary teams, those issues have to be addressed. So, after seeing this, how we solved it, how we, as doing the game engine, how we solve this problem of interoperability between JavaScript and C++ for scripting. We saw first we looked for a tool, and we saw that there is a lack of standard for interoperability between languages. So there is no standard for that. Also, trying the alternatives, we saw that they were hard to work with, or it required this boilerplate that we were avoiding. We were trying to avoid. So we thought, okay, we need to do it ourselves, and it needs to be easy to mix languages. That is why we created MetaCall. What is MetaCall? MetaCall is an open source polyglot runtime that allows you to do this. It allows you to do transparent calls between languages, and you don't need to do any boilerplate to do it. And right now, I'm going to show you right here that you see a require from a module that is written in Python, and just a Python code that does a sum, and you can use it on your Node.js code. So I've prepared some demos here. I have 3 demos to show you. I have the first one that is the simple sum example that you saw already, but you will see it in action. The second one is mixing callbacks. That's interesting because MetaCall allows you to send a callback to another language. And the third one is a machine learning Python from Node.js. Okay, let's jump into the demos. First, let me show you the code. This is what we already saw, but let's see the index. I think I can do this larger. Yes. For this example, we include the sum that is written in Python. And in Python, you will say from Python, and then print the two numbers so we can see the type there, and then return the sum. Let's see how it works. And that's it from Node.js, and then from Python. 3 plus 4 is 7. That's the end of the first demo, but we will do the second one. Let me show you here how this demo is, and I guess, yes, the module that we have is the app.js. Let's see what's going on here. We have a console log and a operate numbers. It seems like it accepts an array of numbers and then a callback. This is a module that it was required from Python. Okay, let's see what's going on in the Python module. We have a function that is operate numbers, and this is the function is the same as doing a map in Node.js for those Node.js developers. It takes in the numbers and then it runs the callback for all of them, and then returns the mapped, that is the 1-4 with an append on an array. Let's see how it works. MetaCall app.js, and there we go. We just passed a function here, and we can do it again because I like doing this stuff. 11, 12, 13. Those are the things. Crazy things are happening here. We have a callback that is getting passed into the Python module. The Python module is executing that code as if it were Python. Pretty cool, right? And we have the third demo now. Okay, the third demo is a machine learning demo. Let me tell you about this. This is a polyglot machine learning application for scraping similar news articles. It is made by one of our contributors. This is how big we have grown the last years. People are doing demos for us. It takes one URL and gives you back a list of similar pages, right? So let's clear this. And let's see what's going on the app.js. Looks like we read line with a question, and we have that URL here, and we only send it to the similar news that is a function inside a Python module. That's the only thing that we do on Node.js. We are not going to be into the in-depth with the Python code, but you can see here that it's a function that accepts a URL, and it will look in Google and do a prediction for us and return a dictionary that is an array. So let's see it in action. We need to go to this, and we need to do MetaCall app.js. Okay, it will ask you to paste an URL. We don't have any URL prepared, but we can grab one. Let's see. We can go to Google and just the latest news. Okay, not the ads, but Mortal Kombat. Oh, okay. What time does it release on HBO? Let's see how many people is talking about this. We paste this here. Okay, perhaps the documents. Let's see it. Let's try it again with a different one or the same one. No, it seems like this one didn't work.
It doesn't work.
But we can try with the other, no problem. Another news, not Mortal Kombat because it is bad luck. Let's go to this one.
Oh.
And we can use onto MetaCall app.js and paste it. Okay, looks like we have matches. Okay, we have an array, or in this column, the actual pages that are apparently similar or not, depending on the value here. 100 is too similar and 0 is completely different. So let's check this. Yeah, looks like it is talking about the same, right? Okay, this is how powerful MetaCall has become, and this is some of the examples that we have prepared for this demo. But there are a couple more you can check on the repos after this talk. Okay, MetaCall. What are the features? It allows cross-language imports. It supports multiple languages with the same interface. And it is it has a minimal or transparent API, which means that we don't need to add any boilerplate code, and you don't need to use us in your code. End-to-end interoperability which means that you can do the same that we showed today, but from Python. You can call Node.js functions from Python as well, and you can call Python code from Ruby, or you can call Ruby from whatever. You can use which language you want to call the others. So I'll give you Vicente now the voice, so you can start talking about more in depth of MetaCall.
Hi everyone, I'm going to try to explain MetaCall in depth. So first of all, I want to explain you how was the state of the art of interoperability when we started this project. So first of all, we had, for example, in .NET, we have component object model, which basically allows us to implement a library in C# and then use the same library in Visual Basic, or vice versa, without any problem. This is quite good, but it's only for .NET. Then we have LLVM, which is a compiler backend for many languages, for example, Rust, Julia, and others. And this allows us to have an intermediate assembly format. And then we have WebAssembly, which is more modern, and it wasn't developed so at this point when we started, but nowadays it still has some drawbacks because you at the end have to implement compilers for all languages following all the features of each language, and that's hard to follow and to re-implement. In another hand, we have, for example, in networking, we have models like Corva, which basically, through code generation, allow us to use objects like if they were in the same process or in the same source where you are coding, but maybe they are just in another computer. And it makes it transparent, but it's still very complex. And for example, we have in proof assistance like which implements program extraction, which is basically a translator from one language to another, allowing us to translate programs in a human-enabled way. But still, it's a bit complex because and it's complex per se, and it only supports some languages like Scheme or Camel. And we have here the architecture of MetaCall. And basically, we have a standard C API, which is AVI stable. Then behind this, we have a meta object protocol that I'm going to explain later on. Then we have the loaders, which I'm going to explain too, and the ports. So first of all, let's go with the ports. Basically, the ports allow us to offer a MetaCall API to other languages, like you see, for example, in the demo that Jose did. Then, as I said, they expose the C API and functions to the other languages, and whenever it's possible, sometimes the language is dynamic enough that allows us to do monkey patch through the API of the language itself. So as you say, we are requiring, for example, a Python script, which it shouldn't be possible, but we do that thanks to the monkey patch. And all of this is implemented in the port. Then we are going to talk about the MetaObject protocol, which is the core of the tool. And for example, here we have the representation of a number in JavaScript Object Protocol. It's called number, and it's basically a 64-bit floating point. And in the same way, we have our own representation, which is our own MetaObject protocol, which is our C representation that is basically a double, which is again a 64 floating point. And then, for example, in Python, the same type is called float, which is again the same kind of value. And in the same way we have native values, we have also complex values. For example, we can support objects in JavaScript, which are called maps in our MetaObject protocol, and they are called dictionaries in Python. And what we do is an abstraction of all these kind of representations between languages through our own MetaObject protocol. Then we have the loaders. The loaders, basically, they are responsible of embedding languages into MetaCall. They have a shared interface that it's a standard. So the good thing is that anybody can implement its own loader for any language, and they have a common interface that you can follow. And they are basically plugins that MetaCall core loads lazily when it needs in order to support some language or whatever you need to support. And as I said, MetaCall loads them during the execution, and they are lazy loaded. And in the other hand, we have serials. I mean, this is a very small overview. It's in fact very much bigger, but these are the main parts of the core. Serials is just another kind of plugins that implement serialization, but it's not serialization between MetaObject protocol and other types, because that's done at binary level. It's just serialization. For example, if you want to export the MetaObject protocol in a human-readable form. So we have, for example, RapidJSON and cprintf, which are just serialization formats. And now we are going to focus in the node loader and the node port, which virtually implement full support to the language, as Jose said, end-to-end interoperability. So we can use any language from Node, and we can use Node in any other language we want. So this is the interface of the loaders, and we have init, load, discovery, clear, and destroy. Basically, in the init phase, what we do is we just start the runtime, we start V8 and leave UV. In the load phase, what we do is we create handles, which is a standard name that we thought because in some languages, for example, C#, they are called dels, and for example, in other languages, they are called scripts, so we call them handles. Then in the discover phase, what we do is we take the functions and we introspect the information of those functions in order to populate all this information into the MetaObject protocol. Then we have the clear phase, which basically unloads the handlers that we load before. And then we have the destroy that basically cleans the resources and exits from the event loop. Some problems that we had in the Node.js loader. First of all, when we started, only the 8th version of Node.js was available. And at that point, we didn't have a proper embedding API until the most recent versions. And on the other hand, we didn't have a way to asynchronous call from C to JavaScript until the 9th version or 10. So it worked, but it was highly unsafe because there wasn't proper synchronization between BA thread and leave UV thread pool. Sorry. And in another hand is that Node has been highly developed and the API has been changing a lot. So it's hard to keep it track and keep, follow it. So due to the lack of embedding API, we only have one method that is called node start, that if anybody has developed in C and C++, basically it's like a main function. It's like it just accepts the command arguments, and you don't have any control over the environment. The environment basically is the V8 instance and the event loop instance. So there's no way to control it. So in order to overcome these problems, we should bootstrap in some way the environment. And in order to do this, we have two different elements, which basically the first one is trampoline, which allow us to return the control from JavaScript land into C land. And the other is called Bootstrap.js because this is the entry point of the embedding phase that we have implemented. So I'm going to explain the start phase. In this part, as we don't have any support for the embedding, what we do is we basically trick Node in order to tell him that he must load Bootstrap.js at the beginning, like if you were doing Node Bootstrap.js. So once we do this, Node will start with this script, and then we will use, through the trampoline, we will be able to register the interface back into the host, which is the Node loader. And then we can pass there the environment and the pointer to the V8 and everything we need. So this is the main point or entry point of the Bootstrap. So you can see in the third line, we have here the trampoline which we are loading with like a binding. We initialize it before launching the start, so we can then access it now in Bootstrap. And now in the following line, we can see that what we are doing, we are calling trampoline register, which is a function that we have in C. And then the first and the second parameters are basically the node loader pointer and another pointer, which is basically the register function, which will provide us a mechanism to do dependency injection, basically. And then this is an API that we implemented in JavaScript that is basically, instead of implementing all the logic that we need in C and C++, as we don't have a lot of control in C and C++, we prefer to do that in JavaScript. And then all this gets passed to C and C++, and then we just call from C and C++ to JavaScript, and we do whatever we need. So I'm going to show you now the trampoline. Once we call to the register, we arrive to this function. And basically what we are doing here, in the first parameter, you can see the imp pointer, which is pointing to the Node.js loader. The second one is the environment, which is a standard structure that NPI uses. It contains the v8 pointer and the livuv pointer, and the third one is a pointer to the object that you saw before, which implements the API in JavaScript. And the register pointer that you are seeing here, which is the function that we are calling, is the second argument of the register, which is the dependency injection point. And basically, what we do when we register, we take all this information, we store that information into the node loader, and then we create some queues in order to be able to later on call asynchronously from C to JavaScript. And that's what will keep the event loop running, because that are basically async resources loaded into the event loop. Now, I'm going to show you basically, once we do all this, we can now start calling into JavaScript. So, for example, what we call at the beginning is the initialize function, which we use to bootstrap the port that we will explain later on. And it basically preloads the port, and that's it. It's something very easily, but you can see at this point we can already call from C and C++ to JavaScript, which is what we want. Now let's go with the load phase. We have two APIs. The first API is basically loading from file, which is basically the required of Node.js. And we have here the function that takes an array of paths, and then we iterate this array of paths, and basically we use required in order to load them. And then we store them into an object called handle, which is basically an array of modules that we pass back to MetaCall. We do the required there, and we store here the modules, and that's it. And we have another API, which is load from memory. And in this API, what we do is we take a buffer, which is basically a string. And in order to simplify this, it's basically an eval. This is just an eval. So what we do is we use the module private API, and we use compile in order to compile the buffer. And again, we store this information into a handle, and that's it. And we return this handle. Now the discovery. This is a very interesting part. We are using a library that is called Chero, which is basically a parser library for JavaScript. This is an old and deprecated library. We may change it in the future for Acorn or any other parser. But at that point that we implemented this, this was a working library, and so we use them. And what we are going to do is to take the function signatures, so we can later on provide type safety. For example, in JavaScript, we don't have types, but it is interesting for cases like TypeScript. And another thing that we need here is to take, another thing that we can do once we have this information is we can generate the bindings in other languages. As, for example, we can make a transparent API in Python in order to call Node.js, because we have this information of the functions. And also we need the pointers of the functions in order to do the calls. So we have here a small snippet that explains it. So first of all, we load the abstract industry from Chero, and then we basically parse it in order to get the information of the arguments, and then we just get this object, which is the discover, and we get the pointer to the function. We get an array of arguments with their name and in type information, if any, and we detect if it's an asynchronous or not function. So now I'm going to explain you the calls. In the discovery phase, we have the function pointers, so we can use them in order to call the functions. On each call, what we do is we do the call with the meta object protocol in MetaCall format, and then we transform into MetaCall representation, into Node.js representation. Then we do the call, then we get the result in Node.js representation, and then we go back to meta object protocol representation. And that's why we can go all the time from one language to another, changing between the same standard language or representation. As I see, we take the argument, we convert it, and we execute the call. And here's the code. Basically, we iterate the arguments, and in this function, we transform in the meta object protocol into an NPI. Then we use this and the pointer function that we saw before, and we pass the arguments in the node format, and then we call to the function pointer, and this returns our information into the function return, which is the result of the execution. And then we do the opposite. We take this from NPI format into MetaCall format again, and we return this. Now, the callbacks are a little bit tricky because it's more difficult to implement it. And basically, what we do here is we always, all the callbacks that you get from MetaCall, all go to the same C and C++ function. And this function is an standard point that we use in order to jump there. And from there, we do the call again to the MetaCall function. So basically, what we do here is we take the argument, which basically is a function, which is a meta object protocol function. We store it in the closure and the pointer to the node loader, and then we pass this. We create a JavaScript function binding this closure to the function in C and C++ that we are seeing here, that is called node loader NPI to value callback. So basically, what we are doing is we receive the call, and in the call, this is the same as in the call that I explained before, but it's symmetric. This is the opposite as we talked before. Instead of receiving the values in meta object protocol, we receive the values in NPI format. Then we transform them into MetaCall format, then we do the call, then we receive this information in the return value in MetaCall format, and then we change again into NPI format, and then we return that. It's basically the same as the call, but in the opposite way. And then we got the promises. The promises are much difficult to implement, but basically are very similar to the callbacks. So basically what we do is we take the trampoline and we hook the resolve and reject callbacks. So they, instead of going through JavaScript, they always go back to C and C++. And once we have the calls in C and C++, we can call back to the implementation of this resolve or reject callback. It doesn't matter if it is in C and C++ or is it in another language. So as you can see here, in the third and fourth line, we execute the resolve and reject of the future, which is a promise. And then we use the trampoline to call back to C and C++ with resolve and reject information whenever we need. And then the destroy. The destroy is a little bit complex too, but I'm going to try to explain it. So basically, we have to track the amount of resources that we have, and that's impossible to do with a async hook library because the garbage collector it doesn't always trigger the destroy of the async hooks. So instead of that, what we try to do, we hook into the event loop. So in each iteration, we track if there is any async resources related to the end user. And then what we do is once we register, we count the amount of handlers that we are using, and we track. And this is our empty event loop for us. Even if, for example, 10 async resources that are required for MetaCall to work. Then when we trigger the destroy, if we don't have any user async resource, we can destroy safely. But if we have some async resources, what we do is just we hook into the event loop, and we check in each iteration if it's empty or not. And we do this with prepared handle, which is not available in Node.js. It's not exposed, but it's a very basic API of live UV. So basically, what we do here, it's before the IO polling, we check again if the user has any async resource. And if it doesn't have any async resource, we execute a callback in order to destroy all the resources that MetaCall has. And then you can see here where the event loop does each iterations. And in the line 6, here is where we check each time on each iteration the amount of resources, async resources that the event loop has, and that's how we safely destroy the event loop and how we hook into the event loop. And then we have the node port that was explained before. We implement the monkey patch here, which is in order to make the API transparent. And this, as I said before, implements end-to-end interoperability. This is, for example, using the API, and we use MetaCall and MetaCall load from file as we saw before, but this is much better because with this, we don't have to use any API. When we require, we monkey patch, and then we can directly use some without using any API related to MetaCall. And then we use the initialization as before. We load a binding, then we expose the MetaCall C API to JavaScript. And we do the monkey patch, which basically is with the introspection data, we can generate all the calls and we return the information like if it was JavaScript functions, but in fact, it can be a MetaCall function or whatever. But for doing that, what we do is we override the require and that's it. And this is an overview that what happens under the hood when we execute this information. So basically, we load the script, and this does a lazy load initialization. Then we initialize the node loader, and then there is the require. So we need to lazy load the Python loader. Then the Python loader initializes, loads the script, and then discovers the information. And then we have the sum function discovered, so we can return it to the JavaScript. And then from JavaScript, we execute the call directly, and this goes to the Python side. And then, well, at the end, we do the discovery in case that we have some exports in this module, and we want to use this in another script. Any questions?
Yeah. Do you hear me, guys?
Yes.
Yeah. So there are a few questions. As I understand, after this small question-answer session, we are going to talk about the function as a service. Is it right?
Yes, that's right.
Okay. So the first one is how many languages currently supported?
We are supporting now C#. Well, it's different because we have some loaders and some ports. From the point of side of the loaders, we have C#, TypeScript, JavaScript, V8 standalone, Node.js. Well, I don't remember, but you will see the repo later on, so you can check it there. And then from this point of view of ports, we have Scala, Rust, D, of course C and C++. Well, and we are working right now with WebAssembly and LLVM, so we can support much more languages. So that's more or less what we have now.
Sounds cool. Yeah, and how does actually MetaCall understand which language loader it should to use? I mean, by the extension's name or by some meta information about the file?
We use a tag to represent the loaders, and what we do is in the ports, depending on the extension, we check if this extension is supported in some loader, and then we use the tag of the loader to load it.
Okay. You actually mentioned that you scrape collect some information about the like function signatures to create bindings for the file and actually to have more type-safe runtime. How does it work with TypeScript or Flow with JavaScript, for example? Do you plan to support TypeScript, Flow.js declaration files, for example, to collect this type information and use for bindings?
We have two kinds of, let's say, execution. The first one is we do type correlation. Let's say if you try to do a call and you're expecting a number and you pass, for example, an integer, I mean, you're expecting a float and you pass an integer, we do the transformation of this for you. So this is like how JavaScript works. We know the type correlation. And we have another way that it's basically if you don't have the possibility of transform the type, we throw an exception and basically that's how it works. That's for dynamic languages, and for static languages, we are thinking other ways that notify in some way the compiler so it can know at compile time those types, but this is experimental yet.
Mm-hmm. And it's like related question, but can we collect types and interface from other language? For example, I want to take information about interface from a C# part of my project and export it to, for example, TypeScript part of the project. Can we collect this information and use it?
We support objects, classes, functions, and features. And I'm not sure if you support something more, but what we are thinking now is in order to support languages that have a lot of type freedom, let's say like proof of systems, we are looking to implement a type, let's say a meta type. So you can program your own types and then export them to other languages, but it's not still implemented, but we are looking for it.
Cool. So for now, that's all. Let's continue.
Yeah. Now I'm going to let Jose show you what we can do with MetaCall in production.
All right. Thanks, Vicente.
Thank you.
MetaCall in production. All right. We know now that MetaCall is that what MetaCall does and what MetaCall allows you to do. So we think that MetaCall can be used for simplified code basis migrations, as we speak before. We know that can be used for monorepos. So you can use all of your languages in one single repo. So you don't have to have different projects going on. And you can interconnect different technologies in the same project. But because MetaCall core scrapes all the information about the functions, these signatures, inside each language, we can use this information.
Can we see the slides again? Because I think it's not.
Yes, it would be good if we see the slides.
Can you turn them on? Oh yeah, thank you.
Thanks. Because MetaCall core scrapes all the information about the functions, we can use this information to deploy your code. And that's where we created a MetaCall function as a service. This service we have implemented with MetaCall core as the runtime to build comfortable deploying system. We've implemented it as a high performance service with server, which gets deployed into a Kubernetes, into a cluster. So let's see it. Let's see what it provides. MetaCall Fast provides automatic API generation, high performance execution, zero DevOps cost because you don't have to do any coding. You just use your exported functions, and zero vendor locking. That's for the same reason. Let's do the demo. This is the dashboard I present to you. What we can do here is to deploy in one of our empty launchpads that we have here. And it gives you two options. One is to deploy the repository, or the other is to use the one zip. You can drag and drop. We will going to use Ramda. I don't know if you guys know Ramda, but it's a library that allows you to do many things. I'll use this Ramda.js that we have here in a zip. This Ramda.js is the distribution version of Ramda, and the only thing that we need to do is select the file. It will automatically create for us the MetaCall JSON files in order to deploy into our FAS. And we don't need the static file, but we will need the Node.js. So we can get rid of the static file, and we just click deploy. Meanwhile, it's loading. We can discuss which Lambda should we use. This will create one specific endpoint for each of the exported functions with their own structure for the parameters. So we will have, for example, the add function of Lambda will be exported as an endpoint. So we have now converted Lambda library into a distributed system. Okay, we have the add. Yes, we have the add, and we have one URL. So let's use this URL to call. Oh, I've tested it before, don't see it. Okay, we have here, and we will do a simple call with a post to this URL that you saw, and with this signature for the A and the B that you see here. So if we call this function, it gives us 65. So this is how MetaCall fast works, and this is how easy you can deploy this amount of functions in Node.js, or you can use any other language that we support, all in the same repository or zip. So, any question, guys?
Yeah, actually, we have, I think, more questions than we have time. Yeah, but I will try to ask only one. So, am I right if I will say that you scrape the information about the exported functions, and we don't need to add some code to annotate that, okay, I need to use this function. The only which we need is to export the function, and after that, at the discovery stage, you will scrape this information and we'll use it in your
You don't need to do anything. That's just Lambda as it is. With the module exports, it generates all the Lambda functions, and basically you are building a distributed systems by just uploading a library. It's very simple. It's the simplest way that you can do.
Wow. It's really cool. So yeah, seems like we will continue our discussion in the discussion zone.
Okay.
All right,
Yep.
guys. Thank
yep.
you very much. And you have here our
Web page.
URLs, so you can check out the code and the landing page for the FAS.
Okay,
Thank you guys a lot for this so cool talk.
Thank you so much, guys.
Have a good question zone and discussion zone.